Now in lessons 2.4 and 2.5, we're going to have some problems that relate to half-life. In science, you probably heard about this, where you have a substance that has a half-life that is equal to a particular period of time. Well, in a half-life, that means that it's being cut in half. So what do you think? Is this exponential growth or is it decay? As you have said, I hope, it is decay, because B, our growth factor, is a number that's between 0 and 1. So let's try to apply this to a situation. Let's say that iodine 131 has a half-life of 8 days. If we start with 20 milligrams of iodine 131, how much is left after 16 days? Well, anytime you have a half-life situation, because it's being multiplied by 0.5 each time, then it is an exponential function. A, as we mentioned, is the starting amount. So the starting amount given here is 20 milligrams. So A is 20. B is what you're multiplying by, in this case every half-life, and that of course would be 0.5. X is the number of half-lives. And if you think about the fact that one half-life is 8 days, then that means 2 half-lives is 16 days. So to answer this question, we'll be able to do so by substituting 2 in for X. So our answer will be what we get when we take Y is equal to 20 times 0.5 to the 2 power. And that comes out equal to 5 milligrams of iodine. And that's because 2 half-lives have gone by, which means it's been cut in half 2 times. Finally, we want to be able to identify an appropriate exponential function for a situation like this that relates to a real-world situation. In a laboratory experiment on the growth of insects, there were 74 insects 3 days after the beginning of the experiment, and 108 insects after an additional 2 days, which would be 5 days after the beginning of the experiment. So we have 2 ordered pairs. Time, whenever it is a variable or a measurement, will be the x coordinate, because the number of insects depends upon the amount of time. Now, given this scenario, what we're asked to do is first find an exponential model for the data, then from that model determine the initial number of insects, and then use that model to predict the number of insects that we would have after 6.5 days of the experiment. So I didn't copy screenshots of this, but what I did was, in L1, I put my x values, 3 and 5. In L2, I put my y values, the number of insects, 74 and 108. And then, like we were doing in a previous lesson, we were fitting a model to the data, but in the previous lesson, we were fitting a linear model. Here, we're fitting an exponential model. So we'll go to Stat, Calculate, Exponential Regression, which is option 0 in that menu. And we can do the whole L1, L2, Y1, so we can graph the data, graph the exponential model with the data, or we can just dump it in our home screen. When we do that, it gives us an equation in our exponential model form, y equals a times b to the x power, and it tells us that a is equal to about 41.97, and that b, our growth factor, is equal to about 1.208. So notice I've carried at least 3 digits after the decimal point for the growth factor, because I will continually multiply by that number, and if I round it too much, my estimates will be quite a bit off. So there's my exponential model for the data. Find the initial number of insects. Well, of course, that means that's the A value. And the A value that we got was 41.97. Also, we're asked to identify the number of insects that this model would predict after 6.5 days. Now notice, 6.5 days is outside of the range of our data provided because our data only went from 3 to 5 days. So 6.5 days is an example of extrapolation. So we have to be cautious about how confident we are in this estimation. But if I substitute 6.5 days in for x, I would find that this model would predict the number of insects would be about equal to 143.3 insects.